so this is chapter 2, section 7, and it's called Freely Falling Objects, and we'll talk about it in terms of its free fall. So in this particular couple of sections, we use the same 4 formulas of constant acceleration that we used before, but now what we're going to be doing is we're going to be going vertically. So last bunch of sections we did, we talked about going to the right was the positive x direction and going to the left was the negative x. Now we're going to be talking about this. Going up is the positive y and going down is the negative y. And we call this the Cartesian coordinate system. So the Cartesian coordinate system is basically the x and the y axis that you would use in almost any math class. And what we'll be doing is we'll be talking about an acceleration due to gravity. And on the planet Earth, the acceleration due to gravity is this number where we'll say A in the y direction is negative 9.8 meters per second squared. Okay, the number is 9.8 meters per second squared. So the Earth has a certain size to it, has a certain mass to it, has a certain radius to it, and all of those things coming in together end up giving us something called free fall gravitation on that particular planet, on this particular planet. So the number 9.8 is not important as far as the entire rest of the universe goes, because it exists on Earth. If you went to Mars or Jupiter or the Moon or any of the other things out there we could get to, the number 9.8 wouldn't be involved, most likely. Okay, so we get this number 9.8 based on our planet. It's based on the planet's size, it's based on the planet's volume, it's based on the planet's mass. And that's how this number comes about. So what this number means is the Earth is always trying to accelerate everything towards it. So if I were to step off of a curb, my body would be accelerated downward because of this thing called the acceleration due to gravity. Okay, so we'll take that into account. And excuse me, just because we say it's free fall doesn't mean the object has to be falling down. Free fall is talking about when an object is exposed to the acceleration due to gravity alone. So if I were to throw something up in the air, as it's moving up, it would be still accelerating negative 9.8 meters per second squared. It would be accelerated towards the center of the Earth all the time. In this case, we would say down. Where's the center of the Earth, no matter what part of the Earth you're standing on? The center is down to us. So I don't care if we go up high and we drop a ball and try to show an experiment as the ball is falling. A lot of people would say, well, that's definitely free fall, and it is. Or if we take a baseball and we toss it up into the air, that's also free fall. That ball, once it leaves my hand, it's going to be accelerating with the number 9.8 meters per second squared towards the center of the Earth. So it has no, it doesn't matter what I'm doing. If I'm throwing something up or I'm throwing something down, it's always going to be accelerated at this rate. And as I said in chapter 1 and as I said in chapter 2, at the beginning, I'm going to use the Cartesian coordinates. So the way I'm going to do this section is anytime the thing is moving up, I'm going to call it a positive, and anytime it's moving in down direction, I'm going to call it the negative. So if I throw it up in the air, it will be displaced in the positive direction. It will have a velocity in the positive direction, but its acceleration will still be in the negative direction because the acceleration gravity doesn't change. If I go high up on top of a building and I let a ball drop down, it will be displaced in the downward direction. It will have a velocity along the way in the downward direction, and its acceleration will still be a negative 9.8. So the good part about this chapter 2 is we use the exact same formulas we've been using all along, and we have to look at some of the subtleties here. The main 2 things that are going to happen is for the formulas of constant acceleration, I'm going to replace the letter A, and I'm always going to be talking about negative 9.8 meters per second squared, as long as I know the problem takes place on Earth. And the other thing I'm going to do is I'm not going to be talking about delta x anymore. Delta x was talking about moving along the x horizontal direction. Now I'm going to be talking about moving along the vertical direction. And so I'll talk about delta y at this point. So just as a teaching moment to see how this is actually all going to work, let's say I have a tall tower, and I take a baseball up to the top of it, and I hold my hand over the edge. So it would be a person's hand hanging over the edge here, holding this baseball. So the baseball is about to be dropped, and the baseball is going to fall through the air. And you could be asked typical questions like, how far has the baseball moved after 1 second? How far has the baseball moved after 2 seconds? How far has the baseball moved after 3 seconds? And so forth. You could be asked something like, what's the velocity of the baseball after 1 second has passed? What's the velocity of the baseball after 2 seconds has passed? And so forth. So what I want to do is just, plug this in. So the first piece I'm going to do is find the displacement after so many seconds. So if the question is, what's the displacement after 1 second, I would use a formula like this. Delta y equals v initial t plus 1/2 a t squared. The initial velocity is 0. When you start something from rest, you say it's starting from 0. So I would say 0 meters per second. Here I would have 1 second plus 1/2 times a negative 9.8, and I'll times that by 1 second squared. So when I plug in these numbers, this is 0, this is number negative 4.9, and when you square these values, it becomes 1, the number becomes 1, and the unit becomes second squared. And as you can see what happens here, it becomes negative 4.9 times 1 is negative 4.9. So this ball has fallen a distance of 4.9. So I'll just put a little mark here. So it's dropped down a distance of 4.9 meters, and that's where it would be at a time of 1 second. This would be a time of 0 seconds. I could do that endless times just to try to show you what's going to be happening here. So if I were to change this number to 2 seconds, then basically I could do the same exact formula, but I just have to change the time frames to 2 seconds. So if I could just erase a moment, I could change this to 2, and I could change this to 2. So this would become 2, and this would become 2, and you take 2 and you square it, and you'd get 4 seconds squared, and 2 times 0 is still 0, and 4 times 4.9, this becomes a negative 19.6 meters. So after 2 seconds of traveling, it'll fall a total of 19.6. So from the top, it'll go all the way down to, call that 19.6 meters. 19.6 meters, I meant to say a minute ago. So that would be the ball at a time of 2 seconds. And again, we could just keep doing this. And we could say what happens after 3 seconds. So let me quickly change it to 3 seconds. Getting all messy here is what's happening. So this would be 3 seconds. This would be 3 seconds. This would be 3 seconds. Take 3, square it, you get 9. Take the unit second, square it, you get second squared. This becomes a number negative 44.1 meters. So after a total of 3 seconds, the thing's going to drop down quite a bit. So after 3 seconds, it's going to go all the way near the bottom. It's not to scale here. I've run out of room to get it to scale here. But it's about 44.1 meters. And the downward piece is what's reflecting with this negative. So the ball would be down here. So this is at time of 3 seconds. Let me just move this other one a little bit to scale more, because if this was 44, then about half of it would be around 22. So this should be a little bit higher up. Let me put this one just up a little bit more. Okay. So this would be the time of 2 seconds. So what you can see has happened is it's fallen, and as it's falling, time is changing. The microphone cord is tangled up with everything here. So as it's falling, time is changing. So in this first distance, it fell 4.9. In the second distance, it fell 19.6. In the third time, it fell a distance of 44.1. If we divide each of these numbers by this number, 4.9, trying to normalize it, it's called. If we divide that by 4.9, we get 1. And if we divide this thing by 4.9, we will get 4. And if we divide this thing by 4.9, we will get 9. Okay? So what it's telling you is that as this thing falls, in the first time frame, it'll fall a certain distance. In the second time frame, it'll fall 4 times that first distance. And in the third time frame, it'll fall 9 times that third distance right there. And that's the whole idea of having a displacement based on a time that's squared. So you see, it'll keep on falling, but it's going to start falling further and further and further each second as time passes. Now, so let's say we have a tower. And let's say it's it could be any number. Let's say that this particular tower is 20 meters tall. So from here to here, it is 20 meters tall. And let's say we hold a baseball out on the edge here, right at the edge. So someone's holding their hand with that baseball, and we're going to release it from rest. Okay. My question to you is, find the time it's falling through the air, and find the final velocity. So these are 2 questions, A and B. So this is a sample problem. So we'll call this an example. How's that? So we could write down the givens. If we write down the givens, what I would say is, one of the givens, I would say V initial equals 0. I would say the acceleration due to gravity is negative 9.8, because this is a freely falling object. It's falling only under the influence of gravity. And I would say delta y is negative 20 meters. And why am I talking about negative? Because up here is where I'm starting, and down here is where I'm ending. And to get there, I have to go this way. So you see, I have to follow that downward arrow. So these would be my 3 givens. How would I find the time? So time is the first thing you're looking for. Time is question mark. So how would you find the time? You could use the formula. You can use this formula. displacement. Delta y is v initial t plus 1/2 at squared. We tried to use this formula in the last chapter, in the last section, and it led towards a quadratic equation. And that's not going to happen right here because the initial velocity is 0. So it's going to simplify much, much nicer. So if I write this out, let me see. It comes out to be negative 20 meters equals 0 times a time. And you see, anything times 0 is 0, so we'll just cancel it. Plus 1/2 negative 9.8. And we have the time here squared. So this becomes negative 20 meters equals, this is negative 4.9, and this is t squared. So we have to divide both sides by negative 4.9. So 20 divided by negative 4.9. Let me move it up into this little section a little bit. Let me just do that math. 20 divided by 4.9. So let me move this work here. So on the left side, I'm getting 4.08. Well, when I take meters and I divide meters by meters over seconds squared, the thing I'm going to be left with is seconds squared. And that's going to end up equaling, this side canceled out. So this side is just going to be t, which is squared. And if I want to solve for that, I have to take the square root of both sides. If I hit the square root button on my calculator, the whole thing, when I take the square root, it comes out to be 2.02. Squaring the number is 2.02. Squaring the unit of seconds squared becomes seconds. And that's t. As I started to say, when you take the square root of the number, you get this number 2.02. And when you take a square root of seconds squared, you end up getting seconds. So that's how to do part A to this. Question B asked us to find the final velocity. So we want to now say v final equals question mark. So since we have three things that we were given, and since we found the fourth thing, now we have four things. So we can use any formula that we really want to use. We could use this one, if we trust. If we trust in our past work and we think we got the time correct here. We could say this: v final equals v initial plus a times t. And plug that in. That's one of the most commonly used formulas. I could plug it in, and I could say v final equals v initial was 0, plus a is the number negative 9.8, and t is the number 2.02. Just kind of have to squish it in here. I don't want it to go off screen, so I've shown you. I'm taking negative 9.8 and I'm multiplying it by 2.02. And that goes in those parentheses there. So when I get this, v final comes out to be negative 19.8. Okay, that's how fast this ball is going when it hits the ground. The negative sign here means it's going in the downward direction. Okay, so when they say the word velocity, velocity is a vector. The vector is usually drawn with that arrow over it. I've been kind of messing up here, not drawing them all the time, but it has a direction associated with it, so that's the velocity. If it had said speed, then speed is something called a scalar, and with a scalar, there would be no direction. So if they said what was its final speed, I would just say the number of 19.8 meters per second. That's how fast it's going. My rule of thumb is if you double this number here, you'll get approximately the speed in terms of miles per hour. So this is approximately the number 20-ish. So it's around 40 miles per hour how fast that baseball is going when it hits the ground. Let's do this. Let's say that you had no confidence in your time here of 2.2 seconds. So you didn't want to use the 2.2 seconds. So let me take that off the table. Okay, and let me say, can I find the final speed with just these three things? Sorry, can I find the final velocity with just those three things? And the answer is sure. I would use this formula. those four formulas of constant acceleration. But we have to be very careful with this formula. So for this particular formula, we're squaring vectors. So a vector times a vector, that's what's happening here. This is another vector times a vector. So everything should have these arrows over it. But when you square a vector, it loses, when you multiply a vector by a vector, it loses its vector piece to it. So for this particular case up here, we're going to lose the vector piece. We're going to lose the sign to it. So you're going to see what's happening. Okay, so let me just show you. So if you plug this in, it would be v final squared equals, the initial speed was 0. So 0 squared is still 0. Plus, I'll put the 2 here. It's the number in front. A, it's negative 9.8. And again, I'm running out of room, so I'll put that tiny parentheses there. Delta y, the ball is falling down. So because of delta y going down, I'll put in the negative 20. And I'll smush that right in there. So it's going to be 2 times negative 9.8 times a negative 20 right in here. And that's going to give me v final squared. So v final squared equals, let me just multiply that. That equals a positive 392. So if we want to and you know, if you didn't put this height thing as if you didn't put that delta y as a negative number, if you were a positive number, then you would be trying to take a square root of a negative value, and that's impossible. We can't take a square root of a negative number. So if I square root both sides, what comes out is it's going to be v final equals 19.8 meters per second. That's what's on my calculator screen. So if you think back to just a few moments ago, I did this exact same formula. I got the exact same number, but I got a negative in front of it. So where's the negative in front of this one? Okay. Sometime in life you took a math class and somebody in your math class said, whenever you take a square root of a value, there's always going to be, in front of the square root, a positive and a negative value. So in front of this number we have a positive and a negative possibility. Which one is it? Well, think about it. The ball is moving down. And with my unit of, with the way I do it, using the Cartesian coordinates, if it's moving down, we can only use the negative value. So I have to know enough to put that in, the negative piece, to get this right. Okay, that's how to do this particular problem. So when we're doing free fall problems, what we're going to say is always use symmetry whenever we can. Now, what do I mean about symmetry? Well, if this was the ground and I threw a ball up in the air, that ground doesn't look flat, but it should be. I think the camera is skewed a little bit. But if we take the ground and we throw a ball up in the air, what will happen is it'll go up, and that's a velocity vector representing how fast it would be moving. A moment later it'll be going up at a smaller speed. A moment later it'll be going up at a smaller speed, smaller, and eventually it will stop. At its maximum height, it stops going up, and it's about to start coming down. So it starts to do this. Okay. So what I've done here is I've shown an upward trip and a downward trip. So you see, if I threw the ball up and I said, someone's going to throw this ball, it's going to be up in the air for, pick any number, it's going to be up in the air for 4.4 seconds. So you throw the ball up in the air, and the time in the air equals 4.4 seconds. Well then, what I could say is, the time that it was moving upward should be half of that time, 2.2 seconds. And the time it was moving down will also be 2.2 seconds. Okay? So you see, if you did this as an experiment, at 0 seconds, you throw a ball up in the air. So it's going up, 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 up. It's slowing down, slowing down, slowing down. It'll stop up here. It stopped moving up here. So the time it was going up, right now on your stopwatch, the time would be 2.2 seconds. Up here, the velocity at the maximum height is 0 meters per second. So that's the velocity at the top. Now it starts going down. It's going to go down, down, down. It's going faster and faster and faster when it goes down. Right here, this would be, the stopwatch would say 4.4 seconds. It took 2.2 seconds to go up to the top. It's taking 2.2 seconds to come back to the bottom. We're using symmetry. And we're saying that what we're doing is we're pretending that there's no such thing as air resistance. Air resistance is the air molecules hitting against the object as it moves through the air. And air resistance will make it so we can't use symmetry. So what we do is we pretend there's no air resistance, thus we can use symmetry. So what goes up will come down, and it'll come down in a symmetrical fashion. So if we throw this thing up in the air, and it's going up in the air for 2.2 seconds, it'll come down for 2.2 seconds. So with this particular one, I didn't mean this to be a problem, a sample problem, but we could say, if you threw up a ball, it was in the air for 4.4 seconds, how fast did you throw it up in the air? Okay. So I could say, find V initial. Find the V initial. Well, won't the V initial be the exact same number as when it comes down here? This would be V final. If it's symmetrical, it will. Okay? And do you know enough at this point to figure out either what is V initial or what is V final? Do you know enough to do that in this particular problem? I would say that you do. So think about that for a moment. Maybe hit pause on the tape and see if you can figure out V final. Okay, what you possibly did is this. You wrote down some givens. So possibly you said this. Now, here's what I would do. I would not do the whole trip. To do the whole trip, I think it's a little bit more complicated. I would do half the trip. In fact, I would like to just do this part of the trip right here. I will do this part of the trip. I'll do the upward trip. And what do I know about the upward trip? V initial equals question mark. What else do I know? V final equals 0 meters per second. I'm only doing the upward trip. So you see, when is the upward trip over? The upward trip is over right here at the maximum height. So that means the speed of this thing is 0 at the maximum height. What else do I know? The acceleration due to gravity is negative 9.8. Okay? With those three givens, you should be able to figure out, oh, there's only two givens here. This is a given and this is a given. Let me just erase this little tiny piece here. Okay. What's my other given? I have one more given. The given is the time it was moving in the upward direction is 2.2 seconds. So with these three givens, the time upward is 2.2, the acceleration is negative 9.8, and the final velocity is 0. I should be able to come up with a formula to figure out what the initial velocity is. And the formula I would use would be V final equals V initial plus A times T. The final velocity would be 0. The initial velocity is unknown. The acceleration is negative 9.8. And the time is 2.2 seconds. So when I plug those into my calculator, it's 0 equals V initial minus 21.56. So if I rearrange it, V initial came out to be a positive 21.56 meters per second. So if you're standing on the ground and you throw a ball up in the air at 21.56 meters per second, it will rise up to a particular height. The ball will stop moving up at one moment, and then it's about to start to come back down. It'll come back down in exactly the same symmetrical pattern, and if you hold out your hand to catch it, you should catch it at the exact same speed of 21.56 meters per second. Okay, because we're using symmetry here. What goes up will come back down. So sometimes the word problems are going to appear to give you less and less information. You have to know how to use symmetry and maybe break up the path, break up the complete journey into two separate parts. Okay, so here's a sample problem again. So what I have is someone's going to throw a ball straight upward into the air at a speed of 36 kilometers per hour. And later they're going to catch it at the exact same elevation. At the same launch elevation, it should say. Okay, so they're going to throw it up at one elevation and just catch it at the same elevation. So the first question is find out how high up the ball will go above the hand. So if we write down our givens, B initial is 36 kilometers per hour. We have to convert that into standard units. We can't be using these type of units. So to convert it, I would say in 1 kilometer, we have 1,000 meters. And I would say in 1 hour, we have 3,600 seconds. And if I plug that in, it's going to come out to be 10 meters per second. So my initial launch speed is 10 meters per second. Okay. I could try to graph this thing out a little bit in my mind. I could think, here's the ground. I'm throwing it up. It's going to go slower. It's going to go slower. It's going to go slower. It's going to stop. And that's where the maximum height occurs. Then the ball's coming back down. Very symmetrical. All these arrows are velocity vectors. So you see what's going to happen is I'm starting here. For this particular one, I want to start here. And I want to end this one here. I only want to take half of this journey. So half of the journey would be from the starting point to the ending. Do I know anything about up here? Yes. The speed of this up here is 0 meters per second. So the speed of it up here is 0 meters per second. So V final is 0 meters per second. That is going to be my another given. What's another given? Well, this is moving through acceleration due to gravity. So the acceleration due to gravity is negative 9.8. Okay, so I've got 3 things here. 1, 2, and 3. Can I find the fourth of delta y? Yes, I can find the delta y when it goes from this starting point to this ending point. What formula should I use? I'd use this one. I have the final speed right here, I have the beginning speed right here, I have the acceleration, and I have the delta y. I know 3 of these things, I don't know the delta y, so I'll just plug it in. The final speed is 0. The initial speed was 10. Then I have 2. Then I have the number negative 9.8. Then I have delta y. So this becomes 0 equals, this is 100 meters squared over seconds squared, plus, this would be 2 times negative 9.8 is negative 19.6 meters over seconds squared, and I have to then say delta y. So if I bring the 100 to the other side, subtract both sides with 100, the left side is negative 100, and then I want to divide both sides by negative 19.6. And that's going to equal delta y. And a negative number divided by a negative number will be a positive number. And I will come out with a positive number. It comes out to be 5.1 meters, and it's a positive number. So if the question was, you throw the ball up in the air at a certain speed, and then you're going to catch it at the same elevation later, find out how high it will go above your head. It should have said find out how the maximum height. Find maximum. Right here it should have said maximum. So find maximum height, it will go above your hand. I have a few other questions to ask about this particular one. Another question I could ask is B, what's the total time it's going to be in the air? So to do something like this, you see, I'm not just going to do half of it. Half of it would be from this point up. To find out the total time time it's in the air, I need to say it's going to start here and it's going to end back down there. So I'm going to move this word end. Sorry, it's very, very messy here. And I'm going to write end right here. Okay, so what do I do? In this particular case now, you see, that will change one of these givens. Because I moved the word end from up here to down here, end will become this. V final would be a negative 10 meters per second, because it's going to be symmetrical. So I'll use this formula. V final equals V initial plus AT. I'll say negative 10 meters per second equals a positive 10 meters per second plus a negative 9.8 times T. Subtract 10 from both sides. So if I minus 10 from both sides here, that's gone. And this is a negative 20 meters per second equals negative 9.8 meters per second squared times T. And if I divide both sides by negative 9.8, what I get is 2.04. So the time equals 2.04 seconds. That's the total time it's in the air for. So if it is in the air for that much time, 2.04 seconds, that means it went up in the air for 1.02 seconds, and it came down from the top in a time of 1.02 seconds. So it's symmetrical, but the total time in the air is 1.04 seconds. Okay, here's another sample problem, and this sample problem says throw a ball straight up into the air with a speed of 15 meters per second. What is the time, and then in parentheses, times, when the ball is 3 meters above the launch point? So again, what we're doing is this. Here's kind of a picture of it. Here's the ground. We're throwing the ball up with a speed of 15 meters per second. And then it's going to go slower, and then it's going to go slower, and then it's going to go slower, and then stops. So up here it stops. And then it's going to fall back down. Okay. And it should be hitting the ground here at a velocity of minus 15 meters per second. So it was going up, it went to a certain point, and then it came down. And they're asking it now. I have no idea almost anything about this problem yet. I don't know how much time it was in the air for. I don't know how high up it went above its launch point. But they're asking me this. What's the time going to be when the ball is 3 meters above the ground? So since I don't even know how high it went up, it's hard for me to even draw a line saying where is 3 meters above the launch point. That makes sense. So, well, let's see. If I write down the givens, I'm going to say this. The initial is plus 15 meters per second. And delta y is going to be plus 3 meters. And then I'm going to say acceleration due to gravity is negative 9.8 meters per second squared. So those are my 3 givens, and that's good. So with 3 givens, I should be able to answer anything else at all. So if I'm trying to find time, if I'm trying to find at what time the ball is going to be 3 meters. Okay, so I'm just going to randomly place a line on the board here. Let's just say that this, it might not be to scale, but this is right now at a height of 3 meters above the ground. So you see, we have 2 possible answers, because at one moment the ball here is moving up, and when you're on this side of it, the ball will be moving down. So there's going to be 2 particular different times that this can happen. When the ball is moving up, it'll be here. There'll be a very, very small amount of time when it's going up, and when it's coming down, see, to get to this point, it has to have gone all the way up through the maximum height and then back down. So it's going to be this point. this, what I will use is, if I try to plug it into the formula that it would seem like practical to plug it into one formula right here, it'll lead you towards a quadratic equation, which is not overly user-friendly. So what I might do is this. I might use this formula. I might say this: V final squared equals V initial squared plus 2A delta Y. Okay. I might plug it in. V final squared equals 15 meters per second squared plus 2. A is negative 9.8 and delta Y is 3. Okay. So this is going to be V final, which is going to be squared. This is going to be 225 meters squared over second squared. This is going to come out to be 2 times 3 is 6 times this. This is going to be 58.8 meters squared over second squared, but it's a negative because of this symbol right there. It's negative there. So when I take 225 and I add a negative 58.8, comes out to be V final comes out to be 166.2 meters squared per second squared, and I have to square root it. So when I square root it, it comes up at 12.89. Okay, so I put plus or minus because whenever you take the square root of a number, you have the plus and minus pieces in front of it. So I'm saying that my V here is going to be a plus 12.89, and my V here is going to be a minus 12.89. Okay. And then I want to know how much time it's going to take to get to this elevation. So I'm going to erase what's on the board. And to figure this out, I'm going to use this formula. The most basic formula we have is V final equals V initial plus A times T. So I'll say the final velocity is going to be it's a plus or minus 12.89. So I'm going to say the final velocity is the plus. So I'll do this down here a little bit. I'll say the final velocity is the plus 12.89. The initial velocity is 15. And that's a plus. The acceleration is negative 9.8. And we want to solve this thing for the t. So if I subtract 15 from both sides, this side cancels out. This side will become, this side is going to become negative 2.11 meters per second, and that's going to equal the negative 9.8 times the t. So I'll divide both sides by negative 9.8. And what I get is t will equal 0.215. 0.215 seconds. So if I throw the ball up in the air, when it gets right here, the time is going to be 0.215 seconds. Okay? And then it's going to go up to the maximum height, and then it's going to start to come back down, 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 down. And it's going to hit the ground. But I want to know how much time is going to be right there, so I'll do everything the same, except I will now use the negative 12. So if I plug this in, I have V final is the negative 12.8. That's happening right at that location. And then V initial is positive 15 meters per second. That's happening at this location. And then I'm going to say plus A times T. A is the acceleration due to gravity, and T is what we're looking for. So I will again subtract 15 from both sides. That's gone. So this will become negative 27.89 meters per second, and that equals a negative 9.8 meters per second squared, and you multiply that by T. So if we divide both sides by negative 9.8, that's gone. And I just have to do this on my calculator, and negative 27.89 divided by negative 9.8, it comes out to be 3.05. So this is going to be, the time is 3.05 seconds. If you ever got a negative time, it's something wrong. You can't get a negative time. Right here, we would say the time on the stopwatch would be 3.05 seconds. And that's the two different values. So we have, they were asking what is the time, and then in parentheses times. So we've got them both. When it's going up at 0.215 seconds, it'll be 3 meters above the ground. And as it's coming down at 3.05 seconds, it'll be above the ground in exactly 3 meters. We have no idea how much time it's in the air for altogether. I kind of have an idea, a little bit of an idea. I don't know if you do, but since everything is symmetrical, if it took 0.215 seconds to go up here, then later, if I know the stopwatch would read 3.05 right at this point, it's going to take an additional 0.215 seconds to go down there. So it'll be in the air for approximately 3.22 seconds, which means it's going to go way, way up higher than this. This is not a good scale at all, what I've drawn. Okay, but that's how to do this particular problem. So for this particular sample problem, I have this. There's a bullet that's going to be shot straight up into the air at 80 meters per second, and the bullet will land in a 20-meter deep well next to the launch point. Find the final velocity of that bullet. So what's happening is, there's something a gun is being held over here. It's going to fire this physics test bullet, and the test bullet is going to go straight up. So it's going to go up, and then up a little bit slower, and up a little bit less, and up a little bit less. And the velocity keeps on decreasing until we finally get to 0. Then it's going to come back down. It's going to go faster and faster, very symmetrical as it's coming down. And it says there's a well beside it, and they said this well here is 20 meters deep. So we're going to compare from the launch point, which is right around here, start, and down here is going to be the end. And we want to figure out what's the velocity of that bullet. So what you can do is write out the givens. The initial velocity is plus 80 meters per second. The final velocity is what we're looking for. The acceleration due to gravity is negative 9.8. And the delta y is going to be negative 20. See, we're starting here, we're ending here, so we're only concerned about going down 20. Now, there's a harder way to do this versus an easier way. The harder way would be to track the bullet the entire time. If we track the bullet the entire time, then it's going to go up, 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 up. We'd have to figure out how high it went up here, how much time it took to go up here, how much time it took to fall back down here, how much extra time it took to go to the well. We don't need any of that. Depending on the question, this particular question said, just find the final speed of the bullet. So you see, we know the beginning speed and we know the displacement. So I will use this formula. V final squared equals V initial squared plus 2 times A times delta Y. I know everything there except V final. So I'll say V final squared equals V initial 80 meters per second. I got to square it. Plus 2. A is negative 9.8. And delta Y is my displacement in the Y direction, negative 20. So V final squared equals, this is 6400 meters squared, second squared. This is plus 392. So this is 2 times 9.8 negative times 20 negative, 392. This is plus a 392 meters squared per second squared. There's a little squared there. I add these together. So V final, which gets squared, is going to be 6,400 plus 390 is 6,792 meters squared per second squared, and then I have to square root both sides. So what's going to happen is it's going to come out to be 82.41. So V final is going to come out to be plus or minus 82.41 meters per second. And which one's it going to be, the plus or the minus, or the both? Well, the ball was shot up. The ball went up, 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 stopped, came down, 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 faster, faster, faster. So this is where it's ending, and it's moving in the downward direction when it's coming down. So we would have to say that the final velocity would be negative 82.41 meters per second. If they had asked us for the final speed, then you could say the number 82.4. But they said find the final velocity, so it's 82.41. But you have to have that negative sign in front.